Hi, thank you very much for the invitation to speak. My name is Ann Almgren. I'm a senior scientist at Lawrence Berkeley National Laboratory, and my talk today is about adaptive mesh refinement, algorithms and applications. And as you can probably tell from the title, one of the things I like is alliteration. And another thing I like is a good read. And I want to paraphrase Haruki Murakami. One of his titles was What I Talk About When I Talk About Running. It's a great book for those of you who have time. And a second title for my talk is What I Think About When I Think About AMR, because I spend probably an inordinate amount of time thinking about adaptive mesh refinement, how it works, how we're using it currently, and how we can be using it. So let me back up a little bit and say most of the problems we solve today are hard. And I'm talking about numerical simulations here. And characteristics of today's problems are often that they couple multiple physical processes across a range of spatial and temporal scales. So for those of you who remember the good old days, they're gone. Gone are the days of simple physics or single physics, simple geometry, single algorithms, and homogeneous architectures. They're gone. So the question that I spend a lot of my time asking is, how do we build algorithms and software for hard multiphysics, multi-scale, multi-rate problems without starting over every time? We don't want to write a code from scratch every time the problem changes. So let me digress a little bit more and say, when you want to design a numerical simulation tool to solve some physics problem, you have to think about discretizations. And the first one we typically think about is spatial. And so I'll say out the gate, not all simulations use a mesh. There's a wide variety of particle methods. And I've grabbed these pictures here off the web and given attributions here, but imagine molecular dynamics. There is no mesh. It's all about the particles and how they couple to each other. But in the world of meshes, for those that do use a mesh, we typically think in terms of structured versus unstructured. And hopefully those of you who do this work kind of knows what those are. There are trade-offs. So in the world of structured meshes, we know that cell I plus 1 comma j is to the right of ij. So it's much easier to write discretizations. We know how to express a gradient, things like that. And once we put it on the computer, we have simple data access patterns. We're doing stride 1 access a lot of our operations. We also get an extra order of accuracy due to cancellation of error, and I'm going to talk a little bit more about that. And there's a way of representing the bounding geometry or objects in a fluid flow, for example, where it's easy to generate the complex geometries through a cut cell or embedded boundary approach. The problem is it's hard to maintain accuracy there. Now, the trade-offs, unstructured meshes, and there's a picture lower left here, you can fit the mesh to any geometry. So there's much more generality, and you don't have a loss of accuracy at domain boundaries because your entire scheme is designed to handle these irregular cells. But you have a lot more bookkeeping. If you take one of these triangular cells in this picture and ask who are the neighbors, you have to store that information somehow. So there's a lot of bookkeeping, and generating the mesh becomes as much of a problem as solving the equations on the mesh. It's much more time consuming. So these are trade-offs. Now, in the world of structured grid, which is where I'm going to go, logically rectangular doesn't mean physically rectangular. So we can use structured mesh and still have some good geometric options. And structured mesh with non-uniform cells, like the lower 3 pictures here, split the pros and cons of structured versus unstructured. So if you look at these, you see that you can adapt the resolution in the mesh, potentially to fit a bounding geometry, like the middle one in particular, or the left side, you might want more resolution at the center. So you still have known connectivity. You could potentially have finer mesh in certain regions, but it's harder to maintain the accuracy. And I keep coming back to this uniform cell size. Why is this good? So for those of you who've taken some equivalent of a numerical analysis 101, this will look very, very familiar. So here I'm going to picture a one-dimensional discretization. So I have points, I'm going to label them I minus 2, I minus 1, I plus 1, I plus 2, and they have a delta x spacing between them. And the way I've drawn them is you can tell the delta x's are not uniform. So I have a delta x left and a delta x right relative to cell I. And I want to write down an approximation for a gradient. So I do a Taylor series. So I say phi, some variable at I plus 1, is phi at xi plus a delta x term plus a delta x squared term, delta x cubed term. And I'm going to do that for the I plus 1 and the I minus 1 cell. And I'll do a center difference. That's a standard gradient approximation at point I. And so I write this down. And what I see is that the centered difference is, in fact, a second order discretization if delta x right and delta x left are equal. And if they aren't, I have a term that's a first order error term. And it might be small, but it's there. So this is why we talk about liking uniform cell size. So we get second order accuracy with this discretization if we use constant cell spacing. And what we'd like to do, where I'm leading here, is to say, I understand that if I want mesh refinement, if I want finer resolution, then I've got to change mesh resolution somewhere. But can I confine this error to a particular location where I don't have to worry so much about doing this everywhere and keeping my order of accuracy? So can we have the best of both worlds? Well, with distorting the mesh, it works for some problems, not ideal, but we can't afford uniformly fine mesh. The concept here is that there are limited computational resources, and we want the most science for the resources we have. And that's where adaptive mesh refinement comes in. So what is it? This is a very brief introduction. So AMR, or adaptive mesh refinement, it refines the mesh in regions of interest. And what you're seeing here is something called patch-based AMR, where you have local regularity. So in every patch, the data is uniform, the layout is uniform. That gives you accuracy, that gives you ease of discretization, that gives you easy data access, things we attributed to structured grids. But that's only true within each patch. Another thing about this, if you look on the left, that's an example from our AMRX software framework. We have black cells, blue cells, red cells, and they're grouped into what we call grids. We use the terms grids, boxes, patches interchangeably. Each patch is regular, but you can also see that we sort of have this hierarchical parallelism, so that we might, for example, I'm getting ahead of myself, but we might want to use MPI across grids and then OpenMP or CUDA within the grid. And the AMR naturally allows for that. The other thing here, this comes back to what I was talking about with the mesh spacing, is we only have jumps in mesh size at the corresponding interfaces. That's code dimension 1. So in a 3D problem, I have 2D faces. In a 2D problem, I have 1D edges. Those are the locations where I have to pay attention to the issues that arise when we change mesh spacing. I don't have to do it everywhere. And you say, well, gosh, if I'm doing all this, why don't I go back to something like unstructured grids? There is metadata associated with an AMR hierarchy, but it's a small fraction of the bookkeeping cost of unstructured grids. Now, I want to compare and contrast here. There are two styles of what we call patch-based refinement. Now, some people would say that the left is patch-based, the right is OctTree. The OctTree people want to be patch-based also, so we've now gone with sort of a level-based versus OctTree. Two things from this picture. In the patch-based or level-based on the left, AMRX, the grid sizes may differ. Not everything has to be a 32 cubed grid. The other thing you see is that a child grid does not have to have a unique parent. And so you see one of those red grids overlays two of the blue grids. So when you're filling ghost cells, for example, you have to look two places, not one. On the right is an OctTree style, and there's a QuadTree. An example, that's the flash code, that every grid is the same size and every child has a unique parent. So when we think about how we organize these, on the left again is this level-based system. On the right is a typical QuadTree discretization. And I know that some folks here are very familiar with that, and I've been looking at some of your work. So both styles break the domain into these logically rectangular grids or patches. Level-based AMR organizes by levels, QuadTree or OctTree organizes as leaves on the tree. And I'm going to focus more on the left. That's the kind I work with, but some of what I say will be relevant to both. Okay, so we've talked about the spatial discretization. You have an AMR hierarchy. You've decided how you want to refine. What about the time stepping? And here I'm assuming that we're doing some sort of PDE for time evolution. We can generalize it. We'll talk about it later. But typically, we care about spatial discretization. We care about temporal discretization. So the fact that you're doing AMR doesn't tell you what your temporal discretization is. It doesn't say whether you're using a first order Euler or a third order Runge-Kutta. That's something that you have to decide based on your algorithm. The only thing we do have to do is make sure that all the data gets to the same time. So when we want to output the data at time 2, all the levels have to have gotten there. But we didn't say how they got there. The big question that comes up with AMR is to subcycle or not to subcycle. So here, subcycling in time means taking multiple time steps on finer levels relative to coarser levels. So for example, if you're a factor of 2 smaller, then you might take twice as many steps. They would be half the size to get to the same time as the coarse grid. So again, there are trade-offs. So if you have the same DT at every level, that's called non-subcycling, then every operation within your advance can be done as a multi-level operation. So if you're doing an advection diffusion reaction system, you can do the advection operation across all the hierarchy, all the 3 levels or however many you have. Then you can do the diffusion, then you can do the reaction. There's a nice sense of all the levels being synchronized when we do that. So that's very appealing. There are trade-offs again. With subcycling, what typically happens is that the ratio of dt to dx stays constant. We'll talk about why that is. And in this sense, you have to complete all the operations on one level before you advance to the next level. So you complete level 0 advance before the level 1 advance. The level 1 advance has to complete before the level 2 advance. So we have this separation of concerns where we have level advance, which is basically what you would do to advance your solution if you only had one level, uniform grid. We have to distinguish that from the synchronization operations. We'll talk more about those. And it can make your algorithm substantially more complicated. And we will allude to that later. So I've just told you it makes things a lot harder. Why subcycle? Well, here's an example. Consider linear 1D advection. We have a constant velocity field u equals 1. I'm going to put a profile, and I have a scalar phi that it's the black line here that you can see that has the sharp edges there. So phi equals 1 from 0.5 to 0.59375, and elsewhere it's 0. I have a second order advection scheme. I'm going to run from t equals 0 to t equals 1. And I'm going to determine a set of dt with a CFL number. That's a corrupt Friedrich-Louis condition. So that would be some number between 0 and 1 times the mesh spacing dx over the velocity. And what I want you to know here is that if you think about without subcycling, if we run with a CFL of 0.9 on the finest level, then on a coarser level where dx is twice as big, the effective CFL is half. That's the thing to keep in mind. What we see in the picture here is that the results of the simple linear 1D advection problem are substantially less diffusive when I run with a CFL 0.9, because I'm running to a fixed time, which means I have to take many more time steps with the smaller CFLs. So if I look at this, I'd really like to run my algorithms with a CFL 0.9. And if I don't subcycle, I can have a CFL 0.9 at the finest level, but all the coarser levels will have much smaller CFLs, and it will be the ratio of the dx of the fine and the coarse level. And here I've assumed factor 2. Now, if all the features of interest are on the finest level, no problem, but we may not want to put everything at the finest level, but we still want to capture the improved properties of the advection. Okay, another reason to subcycle. So I'm making the case here. So let's consider a simulation that zooms in. I'm going to have n refined levels. We'll have factor 2 refinement between levels. And each of them, just for this case, has the same number of cells as the previous level. So in 3D, I'm refining by a factor 2. I will have 1/8 of the physical region refined, but I will have 8 times as many cells per region, so it's the same number of total cells. And I'm going to advance the solution from t to t plus delta t. And this is going to take one time step at the coarse resolution. And I'm going to assume again that I keep dx over dt constant in this. This is with subcycling. And if you look in the chart, levels is the number of total levels. So n equals 0 is I just have one uniform grid. N equals 6 means I've got 6 levels of refinement on top of that. And I ask how many advances I have to do in a non-subcycling versus subcycling. And you see for non-subcycling, I have to do the same number of advances at every level. When I subcycle, I take the total number of advances at the finest level and then half that many at the next courses, half that many at the next finest. And if you look at the ratio, when I get up to 6 levels, it's 3.5. So in theory, my code will run 3.5 times faster if I subcycle than if I don't subcycle. Okay, so that was a cheat. This work estimate's misleading because it only counts what we call the level advance or the single level work. And there's still this issue of the synchronization between levels, and we haven't really addressed what that is. We're going to come to that. Another thing to keep in mind is subcycling is not always possible. If the time advance paradigm is to loop over all leaves of the OctTree or QuadTree, which it is in OctTree and QuadTree codes, then you can't subcycle because you don't distinguish between leaves at different levels. You just loop over all the leaves. Subcycling also requires being able to advance the solution on coarse regions covered by fine grids. That's not always possible. You'd think it always would be, but there are some cases you can't run under resolved. You can imagine, for example, combustion calculation where the equation of state just isn't valid for the kind of values you would get on a grid that's too coarse. So in that case, you've got to run all the levels together so that you can immediately overwrite the coarse data with the fine. Another thing that can kind of be relevant is there are times where if you create a large number of levels, you may have too little work on the intermediate levels. And so you really don't want to spend the time to advance level 1, then level 2, then level 3. If you're subcycling, you have to do that. If you're not subcycling, you can potentially group your tasks in a way to be more efficient. So again, there are trade-offs. And again, it really depends on the system. Okay, what's the takeaway? So one position, which we've actually implemented in one of our codes, is what we call optimal subcycling. So you say we'll subcycle between some levels and not between others. For example, maybe we won't subcycle in a case where we need to overwrite immediately, but we will subcycle where it's a benefit and there's enough work. Another statement is there are options that iterate over levels in a much more complex way. I've given a fairly straightforward example of how people use AMR. There are ways to iterate across the levels in an iterative time-stepping scheme to generate higher order solutions. And what you really want is software that supports both options so that for the particular case you're running, you can explore and figure out for that equation set, for that physics, what is the best way to advance the solution. It's all about getting science done at the end of the day. So now let's talk about coarse and fine again. So regardless of how you time step, you still have to synchronize between levels in some form. Coarse and fine data have to communicate, otherwise you'd be running these as completely separate problems. Okay, so now we're going to go back to our simple cases in one dimension, and this is really how AMR started, was with hyperbolic conservation laws, basically gas dynamics. So let's consider something. I have a solution variable u, it's maybe density, momentum, energy in a gas dynamic situation, and I have a set of fluxes. And u sub t, the derivative, time derivative of u, plus the spatial derivative of x, that's going to be equal to 0. And let's discretize this with an explicit finite volume scheme. So I've written down u at n plus 1, that's time level, minus u at n, is the spatial gradient of the fluxes. And here, this picture, it's a one dimension in space and a one dimension in time. And you can see we have fine cells on the left and coarse cells on the right. So what we want to do to advance this level by level is I look at the coarse grid. Now, those red cells, those were averaged down from the fine, but they're still there. They're still there in the data structures. We can advance them. And then I'll advance the fine grid. And again, the red ones on the right are what we call the ghost cells. Those are interpolated from the coarse data. And let's just think about the same DT at each level. So what we do is we say, let's advance the coarse and let's advance the fine separately. And then ask the question, what is true about the composite solution that may not be satisfied if we advance the levels separately? And when I led off with that Haruki Murakami title, when you think about AMR, this is one of the key questions, which is the two things you need to know to, quote, add AMR to an existing single level method is, one, what do you know how to advance the solution on a single box at a single level? That's the number one thing. Do you know how to advance the solution at all? Obviously, you do if you have a working code. The second thing is, what is true at coarse fine boundaries? And that's a subtle thing in some cases because it's not always obvious what discretization should be satisfied. If you don't know that, you can't design an AMR simulation. It won't take care of that for you because that comes from the physics. So what is true about the composite solution that may not be satisfied if we advance the level separately? So one question, is the coarse data the average of the fine data where possible? Another thing is, did we update the solution with consistent fluxes? And the answer, of course, is not yet. So the synchronization step is about correcting the mismatches. We have to identify the mismatch and then we correct them. So to complete the advance of this time step, we've done a coarse, we've done a fine. We're not declaring ourselves done yet. So first, the most obvious thing is make the coarse data be the average of the fine data where possible. It's very straightforward, average down type of routine. And now this fluxes, if we think about the way that we advanced the coarse cell on the right here was with a flux that lived at the coarse fine interface. That was for cell capital J. For cell little j at the fine level, we advanced that cell and we used a flux at that same physical location, but we computed it differently. So now there's a principle in all of this that we always believe the fine level. So here we want to use the fluxes from the fine level where possible, which means we have to change the answer that we already got on the coarse grid. And this is an operation that anybody who's done this is very familiar with, and it's called refluxing. So what we do is we say, we wish we'd known those fine fluxes when we updated the coarse grid, but you know what, it's okay, we can go back and just fix it. So for that one coarse cell next to the coarse fine interface, we're going to update it. We'll take the value we got, and we're going to add or subtract, depending on which way, the difference of fluxes between coarse and fine. So we had coarse fluxes at that location, we had fine fluxes at that location. We take the difference. We've already computed the fluxes, we've already done the update. So what we'll do is we'll add that straight to the coarse cell at the interface. And now it's as if we'd used the correct fine fluxes the whole time. We're there. So the observation is, in the end, we have exactly the same solution, as if we defined the correct flux at the corresponding boundary before we ever used it. So it's perfect. This was great. Okay, what about subcycling? Well, we can play the same game. And again, in these pictures, x is along the x-axis and time is along the vertical axis. It's a 1D problem. So in this case, our dt on the coarse grid is much finer. You can see that. And again, the red is averaged down from fine. And we have to take multiple steps to advance the fine solution. And so now we take the same principle and say each time step we use to find flux. Gosh, I wish I'd updated the course with the right flux. But that's okay. I can add up those fine fluxes, and they have to be weighted by the dt and the dx. If I weight those correctly and I add those, now at the end of the day, the course solution sees the correct flux. So this works. So subcycling with refluxing gets me conservation. My course will be the average of my fine. It's a very consistent solution across levels. So AMR, piece of cake. Okay, to make subcycling look pretty easy, actually it makes AMR look pretty easily. If you think about more than 2 levels and multiple spatial dimensions, the idea here is you can think of it as a recursive operation that at every level you advance every patch at that level, and you don't know about the final levels, you ignore them. So you have to fill your own ghost cells. You fill those from a coarser level if there was one, or you fill them from physical boundary conditions or from other patches at your level. So you advance that, not seeing the fine level, and then you want to go and advance the next fine level. You have to supply ghost cell boundary conditions to it, so you interpolate in space and time where necessary. You got to keep track of your fluxes, put those into something we call a flux register, and then at that final level you integrate n+1 steps, or I'm sorry, r steps. You integrate those level n+1. Now level n+1, we're calling this recursively, so level n+1 is going to take one step and then say, is there a level 2? Let me go advance that multiple steps. So you do all that, and then when you get to a point where coarse and fine are at the same time t, you average the fine onto coarse, you do this reflux operation, and you move on. And you can end up refluxing between levels 2 and 1 before you end up refluxing between levels 1 and 0 because of how they sync up in time. And you can see that in this lower right corner. Level 0 goes 2 steps, level 1 goes 2 steps. The synchronization at that on the left where the black arrows meet the red arrows, that synchronization is just between levels 1 and 2. When we get to the final time, which is the top of that cartoon, then we sync 2 and 1, and we sync 1 and 0. Okay, not bad. Okay, so that was hyperbolic equations. Everything we did explicit advances, information traveled 1 dt or 1 delta x at most in one time step. Let's think about elliptic equations. So let's take a very simple elliptic equation, Laplacian of phi equals some right-hand side. And for the purpose of these plots, the right-hand side on the fine grid is it's a +1 and a -1, somewhere in the fine region. And when I average those down onto the coarse grid, they cancel out, so the right-hand side of the coarse grid is 0. This is a very contrived example because it can illustrate the point. So if I have a right-hand side of 0 and I have boundary conditions on the left and right, the uniform coarse solution is just a straight line. There is no Laplacian of phi, it's a straight line there. If I solve the middle picture here on a uniform fine grid where I do see the right-hand side, the plus and the minus, I will see what we call a kink, technical term. We see a kink in the middle. And then everywhere else, it's just a straight line. So what happens if we follow our paradigm and we do this, what I'll call here classic one-way coupling, and there's an Enzo code that in particular does this. So what we're going to do is we're going to solve on the coarse level. We're going to supply boundary conditions at the fine level, and we'll supply them Dirichlet, which means the value themselves from the coarse level. And then we'll solve on the fine level. And what you can see, and it's a little bit hard to see, but you see that you have the correct kink in the middle. This is the lower right picture now. But you also have these kinks. You have a change in slope at the coarse fine interface. And using our paradigm, the first thing we have to do to be able to figure that out, to fix it, is to identify the mismatch. So what happened is now I have a second order operator. Now I'm taking a second derivative in space. And that means that at that interface, before all I had to satisfy was the fluxes, now in some sense I have to satisfy Dirichlet and Neumann matching conditions in phi. The Neumann matching conditions are analogous to the flux that we were talking, the advective flux we were talking about. So we have a Neumann mismatch. What happens here is the solution is continuous across the coarse fine interface, but the slope is not. And that's not the correct solution. So we have to ask, what is the analogous reflux operation? We want to fix this. And the way that you reflux for an elliptic problem is that this Neumann mismatch, that change in the slope there, becomes a source term. And if you recall, when we did the advective reflux, all we had to do was say, just add that to the coarse cell next to you, no problem. Here, this becomes the right-hand side, and we have to solve Laplacian of delta phi equals a right-hand side that comes from these mismatches. So we have to solve another elliptic equation, and then we add that solution. And it's a little bit hard to see. The green, I apologize, is a little bit hard to see. The green is the correction that we get. And what you see is that it's non-zero almost everywhere. And if you add the green to the blue, you get the red. The red was the correct solution if you had fine grid everywhere. It's also the composite solution in this case because there's no right-hand side away from that center. And we got there by doing a coarse advance, a fine advance, or a solve, and then a synchronization solve, which was a composite solve. So takeaway from this is, first, you should realize that things are getting a little harder. In this case, the correction is not local. The correction changes the solution everywhere, not just at the coarse fine boundary. And the other takeaway here is that the operation that you do to synchronize the levels depends on what you solve to start with. So we had an explicit local reflux for explicit advance of a hyperbolic system, and we have an elliptic correction equation for solving elliptic system. So that's our introduction to AMR. We've done hyperbolic, we've done elliptic. You can do parabolic equations analogously. Where do we go from there? So let's go to 1998. We want to solve the incompressible Navier-Stokes equations. And I've written them down here. So in this case, U is velocity, rho is density, P is pressure, HU and HC are source terms, C is just a scalar that we want to advance, and we have a div U constraint. I'm not going to go into the gory detail here. I will just point out that this picture was a picture that appeared in the paper we call the AMAR paper from 1998. And this was state-of-the-art graphics at the time. We were so proud of this picture. It's a little daunting to see how it compares to ones today. But anyway, on the left here, I've written down 4 mismatches. And this is how we thought about the AMR algorithm. And it took us quite a while to get this all right. And basically, the four mismatches, the first one looks very similar. It's basically the fact that the coarse data under the fine data needs to be the average. Okay. I'm not going to read these to you, but let me just say that the synchronization operation for level L and L plus 1 says, okay, first, correct for the advective mismatch. Correct for the fact that you flux the wrong amount of stuff across a boundary. Oh, and oh, by the way, you did that for 2 reasons. One is because your advection velocity was a little off, and another because when you constructed the flux, your states were a little off. So there's actually 2 parts to that. But now when we correct that, you know what? We actually got the diffusion a little wrong too. So we have to put the correction for the advective mismatch into the right-hand side for the diffusive mismatch. Then we have to do a solve for all of that. Oh, and then, by the way, you have to take all of those corrections and you have to feed those into a source term for a projection correction. We solve a projection method here to impose div U equals 0, which means solving elliptic equation for pressure. So those corrections have to feed into the projection correction, and it was something. So that was 1998. And that was the incompressible Navier-Stokes equations. Up until then, AMR had been primarily for compressible flows because explicit reflux is a wonderful thing to do. Incompressible Navier-Stokes was a little bit of a game changer for us because it opened a door. Okay, let's fast forward from 1998. We're in 2021 now. Again, AMR has a long history. Compressible astrophysics actually had a lot of applications, other compressible phenomena as well. But now, when I look at the right, the upper right is a combustion example, and that is low Mach number combustion. I'm going to talk about some of the issues with that. The middle right is moist atmospheric modeling. So here, instead of using implicit methods for compressible equations, we're going to use a projection method for it's not incompressible, it's a low Mach number type equation. And the bottom right, I've got low Mach number astrophysics, where we can model convection in stars before they explode. So it's a low Mach number phenomenon. And this is showing it's a precursor to a type 1a supernova where you have heat release in the middle and you get this fluid convection that happens right before it ignites. There are also some solid mechanics example I'll show you a movie of. And oh, by the way, this is just mesh data. We like particles too, so you can add particles to this, and particles can change the solution on the mesh. You can have PIC type algorithms of all sorts of things. So you can have particles living at different levels. And another especially interesting way to use AMR is actually something we call AMAR, and that's adaptive mesh and algorithm refinement. We'll have another example of that. So we've come a long way. As I say, this is not your grandmother's AMR anymore. Okay, so I've talked a little about these low Mach number approaches. You get to a point where you realize if you know how to solve one type of low Mach number flow, and we've been doing this for a while, so we do know at least one approach to it, you can reuse a lot of the software that you build for that. So when we think about low Mach number advances, and this is one approach to it, so the elements of an AMR code for low Mach number simulation for us include the projection method formulation, which can include advection, diffusion, reactions, but then the way that we keep the solution on the constraint, which is div u equals something, or for example, div rho 0 u equals 0 for anelastic, is to solve an elliptic equation for pressure, and that basically imposes the constraint and keeps the velocity divergence free. So that's the variable density Poisson solve. It updates the perturbational pressure and the velocity. We might have an integrator for reaction network. A lot of things we do are reactive fluid flows. And then you throw AMR into that so that you can resolve the range of spatial scales. Lower left picture here is a compressible astrophysics. We're zooming in on the center of a star. You can't actually, we're also picking up some Rayleigh-Taylor instabilities you can't quite see. And the picture on the right is what we call a V flame. And it shows the different grids and how we have more refinement basically where the flame is, which is marked by the blue here. Okay, so we talk about algorithms and applications. I'm going to go through a couple different applications, and each of them introduces something interesting about using AMR. So one of the codes that we have developed is called PeleLM. It used to be LMC for low Mach number combustion. It has convection, species, thermal diffusion, reaction networks, and a lot of physics in there, applications from detailed flame studies to lab scale flames. So what's interesting and what's hard about low Mach number combustion? One of the things that happens is in compressible flow, you take a very small time step. And so it's very small relative to advective timescales. It's actually small enough relative to reaction timescales that you can get away with strang splitting, which I don't have time to go into. What happens in low Mach number codes is you're typically running with a much larger time step, which is great. That's the whole point of it, is to get that efficiency. But now strang splitting tends to introduce splitting errors that you didn't see before. So you have to rethink your entire single level time advance because you're running at a time step that's much larger. And so you have to couple the physics. You have to work harder to couple the physics. Another thing that's interesting is when you do combustion in a closed chamber, the pressure actually rises with heat release. And so you've got to ask, you have this pressure, and the idea is that it's a function of T, not of space, and it rises uniformly. When you do that on an adaptive mesh framework, that mesh hierarchy, you have to make sure that the pressure is the right value at the right time at the right location. A comment here is that this same code framework was extended to astrophysical nuclear burning studies. It turns out that stars burning and flames burning on Earth are actually real similar. Another one I showed you this picture, the moist atmospheric modeling. So one of the things is this has stratified flow, which again is not that hard. What's interesting about this one is that the Clausius-Clapeyron relationship doesn't give you a rate. What it gives you is a statement about equilibrium. It says this is true at equilibrium, and the problem is that the divergence constraint is about heat release. You have a divergence of u equals something, and that something has to do with heat release, but you don't get heat release from the Clausius-Clapeyron relationship. Heat release is based on evaporation rate, and so when you do something with the low Mach number atmospheric modeling, you have two aspects. One is this larger time step, and the second is how do you turn an equilibrium relationship into a statement about rate? And that's one of the algorithmic subtleties with this. So another application, I mentioned the astrophysical convection. So we have a code called MAESTRO for low Mach number astrophysical flows. Looks very similar to the atmospheric flows because it's the stratified background, but it also looks similar to combustion because it has these nuclear reaction networks. And typically we use AMR to either zoom in on the center of the star, which you'll see in that center bottom picture, or on the surface of the star, sometimes for things like X-ray bursts, depending on the applications. So people tend to think, why would you have a low Mach number code for astrophysics? And the reason is there's a lot that happens before the ignition. Astrophysical phenomena, what we see is light emission that happened because there was an explosion. So observables are all about explosions, but what happened before the observable is of interest. So we have these different types of progenitors for type 1a supernovae. We have X-ray bursts, convection, and massive stars. Again, the algorithmic complication is very similar. You have a strand splitting error, coupling error there, and also you have this background pressure. So it turns out that stars, before they explode, they puff up a little bit. Not surprising if you think about it. So in the combustion case, we had that was independent of space. Here you have a combination of stratification and time change. So this is the same picture we saw a minute ago. Okay. Multiphase flows. This has been an interesting one we're doing as part of the exascale computing project. So we have particles in a gas. So you have solid particles in a gas. The solid particles have fixed volume. And the thing about these is we don't consider them point particles. They're particles that take up a certain volume in the fluid. And they also exchange momentum. The fluid and gas exchange momentum by the drag terms. So we have a kind of different set of equations. And this becomes interesting because if you refine the mesh too much, then your particles tend to fill up your mesh. And so it's an interesting problem of, can you refine certain features of the fluid, but maybe not other features? And this is, again, this MFIX-EXA project that I'm working on. This is just a bubble rise that some gas is injected below. It rises through the particle bed, and you can see some of the particles fill in behind it. Okay. So AMAR I mentioned. This is the idea that you have different physics at different levels. And I think there's a lot of potential with this. This example is actually from a ways back, and this is John Bell, Alex Donovan, and Alex Garcia. Consider a DSMC algorithm, that's direct simulation Monte Carlo, in a small region of the domain coupled with a fluctuating hydro algorithm. The fluctuating hydro algorithm is a continuum approximation. Its solution variables on a mesh, but they have some additional terms relative to the Navier-Stokes equations. So level 0 here covers the entire domain. That's the blue grid, and we're going to solve stochastic PDEs there. And the red arrows are giving you an idea of the stochasticity of the velocity field. But you can see that blue grid. There's a mesh there. Level 1 in the center, it's a smaller region, and it's bounded by orange, which is a little bit hard to see. And there we solve particle equations. And so this is interesting because if you think about AMR, things we need to know, again, how do you solve, as I talked about, how do you solve the equations on each level? How do you solve the fluid equations? How do you solve the particle equations? Now you have to say, what is true about the solution at the corresponding interface? And we have some analogies here. So interpolation, or used to just spatially interpolate coarse mesh data, fine mesh data, we replace that by statistical realization. So that's going from mesh to particles. We have to create ghost particles in some form. Averaging is now going from particles down to mesh. So that's a different operation. And refluxing, we have the same concept. There are fluxes that we want to be the same as seen by the mesh and by the particles. So you have to be able to construct a continuum flux from a particle flux. So this is an area where I think there's a lot of interesting work still to be done. Okay, now I get to make my plug. So AMR requires good software support. If you remember my first slide, or maybe a very early slide, where I said gone are the easy days, you do not want to spend your life rewriting an AMR package or reinventing the AMR wheel. There are a number of packages out there, and one of the things they all do is they give you some kind of data containers for blocks of data at different resolutions. Otherwise, they wouldn't be AMR. They do some amount of managing the metadata. So they have iterators that loop over the boxes either at a level or across the leaves on a tree. They manage regridding. How do you create new grids? But there are a lot of differences as well. What types of data do they support? A lot of them have cell-centered data only, which is a problem. What types of time stepping? A lot of them, for example, Flash, are non-subcycling, same DT. Do they support a dual grid approach? Do you have to load balance the particles in mesh? If you have a particle mesh calculator, do you have to load balance those things? Do they have to have the same hierarchy? When we talk about running these really big, really complicated problems, we're talking about supercomputers, which means we're talking about MPI, not just MPI, we're talking about MPI plus X, where X is, in our world, OpenMP on multi-core machines and CUDA/HIP/GPC++ on today's and tomorrow's accelerators. So now we're getting into the computer science side of this. What kind of task iteration support? Do they have support for asynchronous operations, fork join? What do they do for you in terms of kernel launching? How flexible is the load balancing? Can you make it depend on the things you want it to depend on? And what additional features? So I get to make a plug here. So AMRX is the software framework that we are developing as part of the Exascale Computing Project. I'm the deputy director of the AMRX Co-Design Center. And our responsibility is basically to build and maintain and to keep making better a software framework that supports 8 different ECP applications. Doesn't support all of them fully, but it's there. So it is a software framework for massively parallel block-structured AMR applications. It's written in C++11. Actually, we use some more advanced features now with an option for calling Fortran. There's an interesting conversation about C++ versus Fortran if anybody wants to have that later. It supports parallelism through MPI plus X. And again, basically every grid or patch, the data on that patch lives at a single MPI process, but a single MPI process might have multiple patches. And then if you want to loop over the grids and then loop over the cells in the grid, we might use OpenMP over tiles, static versus dynamic scheduling. With GPUs, which is where a lot of our efforts are these days, same concept. It's MPI over grids, but then you send a grid's worth of data, or sometimes a tile, but a grid's worth of data to the accelerator. Actually, it's going to live there in managed memory, but we can think of it this way. And you have CUDA or HIP or DPC++ running on the GPUs. So this hierarchical parallelism, the way that the computers are now built, fits very well with the way AMR schemes work. So we have multi-level mesh data and iterators, multi-level particle data and iterators. A lot of these operations are supported: the interpolation, the averaging, the refluxing, and other things like pick type operations, particle mesh operations. And then it turns out a lot of codes that use AMR need a lot of the same common features. 2 of those are multigrid solvers and this cut cell representation. So the cut cell representation is what I talked about earlier, is how do you represent geometry in a structured mesh code? And the lower right picture there shows a CLR, which is a chemical looping reactor. That's a geometry that we have to solve particle fluid equations in for the MFIX project. So we need that embedded boundary representation. We also need geometric multigrid solvers. So those are part of AMRX. And then we have the option to call external solvers. Load balancing is a big deal. So we have support for multiple load balancing strategies. You can decompose mesh versus particle load balancing. You can have load balancing depend on a number of different things. And then there's a native IO format that's supported by a lot of the major Viz packages. Okay, just a couple comments. So load balancing, a lot of people know sort of the standard domain decomposition. I'll break my domain into 32 grids, and I have 32 processors, and I'll put 1 grid per process. Sometimes that's great, but what happens is a lot of times you really want to balance the work, not just the number of cells. So if I look at this example, this is what we call AMRX Pachinko. It just shows the, let's see if I can get it to come back, the particles dropping down like a Pachinko game. And when you look at this, there are a number of cells in the background, and you actually can't see the grid cells. What you're seeing are the white squares are grids. You could load balance saying every block there has the same number of cells, so I'll distribute those equally. But wait a minute, maybe where the particles are is where the action is, so I should load balance according to that. Or I've got those cylinders there. Well, I've got to do more work because I've got higher order discretizations at those cylinders, so maybe I'm doing more work there. I should load balance based on that. One of the things that we've learned is we could try to be really smart and make a model for the cost and try to figure it all out ahead of time. And one of the things that we've learned is sometimes just asking the code, how much time did it take you last time? And using that as a predictive estimate is the best thing we can do. Another kind of random thing, but it's been very helpful, is what we call grid pruning or mesh pruning. So a lot of times when we think about structured meshes, we're always picturing these rectangles. And for this chemical looping reactor, one of the things you can see is it's got these narrow pipes with a lot of air in the middle, a lot of space that we don't need to resolve. And we're not doing any work there because there's no fluid or particles there, but it's taking up memory. If we had to allocate data there, we waste a lot of memory. So we do one of these things that we call mesh pruning, which is we could just remove those grids from the hierarchy. There's no reason for them to exist. And so we just take them away. And so we can still use these rectangular cells. We're doing everything the same. We've just removed those from our domain. And another thing which people don't typically think about is, I call it AMR for one does not have to mean AMR for all. One of the things we do in the MFIX code is the way that we do particle wall interactions is to define a level set that holds the distance to the wall. And then at a particle location, we can interpolate the level set onto the particle location to ask how close is it to the wall. These particles have a finite radius, so when they get within that radius, they want to bounce off. We want the level set to be relatively finely resolved because that captures the curvature of the interface there. Here I'm looking head on at a cylinder. But one of the things I told you about is I don't want to over-resolve the mesh that is used to bin the particles, because that doesn't work for various reasons. So here we've refined the level set and the mesh that holds the level set, but we haven't refined the mesh on which the fluid and the particles are involved. So there are a lot of games that you can play like this when you have a multiphysics simulation. Some of them need resolution in some place, some of them need other resolution. Okay, with that, I'm going to end. So again, AMRX, it was a long time in forming, and it's supported both by the Fast Math SciDec Institute and by the ECP Block Structured AMR Co-Design Center. For those of you who are into software, it's part of the XSDK software releases and will very soon be part of E4S. Just my final examples here, I've got solid mechanics on the left, white dwarf mergers and astrophysics simulation in the middle, and a compressible reacting flow on the right. Thank you very much for your attention, and I look forward to talking to you all later.